Today, I'm pleased to welcome with us Dr. Alexy Arefiev, who is an associate professor at UCSD. He joined the faculty at the University of California, San Diego School of Engineering in 2017, and he received his Bachelor of Science in Physics from the Novosibirsk State University in Russia, and his PhD in Physics from the University of Texas at Austin. He was selected by the Division of Plasma Physics of the American Physical Society to receive the Marshall N. Rosenbluth Outstanding Doctoral Thesis Award for his work on plasma propulsion. Prior to his move to UCSD, Arefiev worked as a research scientist at the Institute for Fusion Studies and as an associate director for theory at the Center for High Energy Density Science at the University of Texas at Austin. He serves as a co-executive secretary of the Joint Institute for Fusion Theory, which is one of the programs through which the U.S.-Japan Fusion Research Collaboration is organized. So today's talk is going to be recorded. So if you're uncomfortable with that, please log off. And also please be aware it's an unclassified meeting with external people logged on. So please be aware of any export control issues. If you have any questions, please enter them in the chat field and I will read them at the end. And otherwise, I hope you very much enjoy today's seminar. And thank you for joining us. Please take it away.
Thank you. Thank you for inviting me and giving me this unique opportunity to tell us about the research that we've been doing at UCSD. Now, since we're doing this online, there might be some connectivity issues. So if for some reason you're not able to hear me clearly, please let me know, and then I'm always happy to repeat or reiterate. So today I will be talking about laser-driven magnetic filaments, and hopefully by the end of the presentation, I will be able to convince you that they are a promising platform for doing high-field science in laboratory conditions. Now, before I begin, I would like to thank all my collaborators for their contribution, because I will be covering a lot of research that has been done over the years. I particularly would like to highlight the students and the postdocs here at UCSD. I also would like to thank our sponsors at NSF and at Air Force R for supporting this research. So I think it would be fair to say that, at least in part, the interest in high-field physics is motivated by extreme astrophysical environments. So here I would like to start with just a couple of examples. The first example is a neutron star. Neutron stars can generate extremely strong magnetic fields that can be in the range of a megatesla or even stronger. Now, in contrast to that, even with superconducting magnets, we're able only to get to 10 Tesla in terms of static magnetic fields in laboratory conditions. Now, another example is a pulsar. A pulsar is a rotating neutron star. It has a magnetosphere that is filled with a plasma, but in contrast to what we're used to here on Earth, this plasma is produced by light colliding with light. So it is actually an electron-positron plasma. Now, again, in contrast to that, the two-photon pair production has never been observed with real photons in laboratory environments. Now, this huge gap in what is available in astrophysical environments and what we can actually achieve in laboratory conditions is huge, but things are changing in big part due to the construction of large-scale, high-power, high-intensity laser facilities, and people are very interested in bridging the gap and figuring out how these big lasers can be used to probe at least some relevant physics in the lab. A lot of this discussion has taken place recently during MP3 meetings, where MP3 stands for the Multi-Petawatt Physics Prioritization Workshop. We still have a few more meetings to go, and then there will be a final report. So if you're interested in this topic, I strongly recommend tuning in and participating. So now, why is there such a huge gap? In big part, this is due to some serious fundamental obstacles. So in case of the magnetic field, it is the strength of the magnetic field that is a problem. So if we're trying to drive a field that is stronger than 50 Tesla, you can clearly see here on the right what happens to your metal coils. They blow up. Now, in the case of the pair production, we're on the other side of the spectrum. It is the smallness of the cross-section that is really the challenge. It is roughly 10 orders of magnitude smaller than the cross-section for the electron impact ionization. So let me put it in some context. So let's imagine that we have a cloud of gamma rays and their density is equal to the critical density for a 1 micron laser. Then a single gamma ray would have to travel roughly 100 meters before colliding and producing an electron-positron pair. Now, to make things even more challenging, because we are producing matter from light, due to the conservation of energy and momentum, the product of energies for the two photons has to be greater than the square of the rest energy for an electron. So this means that not only that we need very energetic electrons, they also have to be very dense. Currently, such sources of gamma rays do not exist in laboratory conditions, but things are very likely to change due to the construction of the ELI laser facilities. For the purpose of this talk, the ones that are particularly relevant are the ELI NP in Romania and the ELI beamlines in the Czech Republic. They have groundbreaking features that are likely to revolutionize things, and the purpose of my talk is to show you that these features potentially will make it possible to probe high-field physics regimes by overcoming some of the fundamental limitations that we've just discussed. So what are these groundbreaking features? First of all, it is the power that has already been demonstrated to be at the 10 petawatt level. Now, instead of having just a single beam, these facilities have already at least 2 beams that can reach this power, and it is expected that they would be focused on target and reach an intensity that is at least 5 times 10 to the 22 watts per square centimeter. Now, the rest of my talk is essentially an upper-level overview of several interconnected phenomena that can be unlocked by high-power, high-intensity lasers. I will start by showing you that there are certain setups that can be effectively utilized to generate extremely strong magnetic fields inside a plasma. And then I will show you how these fields can be leveraged to produce dense gamma ray beams. And I will conclude my presentation by showing one application that can really benefit from such dense beams of gamma rays. It is the production of matter and antimatter from light alone through photon collisions. Now, when we're talking about generating a very strong magnetic field, choosing the right type of medium is everything. And in this sense, choosing a plasma is very natural because in principle, it can generate and maintain an extremely strong magnetic field. The limitation comes from our ability or inability to generate a sufficiently strong current density. Now, the current density is proportional to a product of the electron density and the electron velocity. Now, since the electron velocity cannot go above the speed of light, we're really limited by the density of the electrons. So, of course, you can choose a very dense material, but the laser should be able to penetrate this material and push the electrons in order to drive the desired current density. And this is where the limitation comes in. So if the electrons in the target are non-relativistic, then there is an upper limit that is set by the so-called critical density. It is only determined by the laser wavelengths. So if the plasma is denser and often referred to as being overcritical, then a laser pulse would not be able to go in. Fortunately, this limitation can be relaxed if we're able to hit electrons to relativistic energies. As the electrons become relativistic, their mass effectively increases, and you already can see from this relation here that as the mass increases, the upper limit will go up. Now, since the electrons are being heated by the laser itself, the upper limit becomes dependent on the laser amplitude. Here it is quantified using this dimensionless parameter A0, where E0 is the amplitude of the laser electric field. So now let's look at some specific numbers. So for ELI-NP, where the laser wavelength is 800 nanometers, the projected intensity is 5 times 10 to the 22 watts per square centimeter. So this would correspond to a value of A0 that is equal to 150. Now this pushes the upper limit significantly up. so that the laser is able to go into a plasma that is 100 times more dense than the classical critical density. So this is why we need to be working with high intensity lasers. Now, when we're talking about driving a field, we're really interested in producing a field that can be considered static, at least on the time scale of the laser pulse duration. Now, in order to achieve this, the electron response time has to be shorter than the laser pulse duration. By estimating the electron response time as 1 over the plasma frequency that scales as a square root of the electron density, we can recast this condition as a requirement on the electron density. Now note that compared to the requirement that we've just discussed, this sets a lower limit on the electron density. And it depends on the ratio of the laser period to the laser pulse duration. Now, again, let's take a look at some specific numbers. So what is interesting here is that this condition enables us to generate static fields for a wide range of laser facilities. So for example, let's take a look at omega EP. Since the laser pulse is 1 picosecond, then this limit is pretty low. It tells us that the plasma has to be denser than 10 to the minus 5 times the critical density. So this means that already using gas jets or expanding plasmas, we can get into the desired regime. And in fact, this has recently been achieved. The publication came out in the New Journal of Physics earlier this year, where Amina Hussein presented some experimental results supported by particle and cell simulations that indicate that very strong magnetic fields were driven in the plasma using this approach. Now, if we're talking about a laser pulse that is much shorter, like in the case of the Eli NP, where the pulse duration is only 27 femtoseconds, then the lower density limit goes up and the plasma has to be denser than 1% of the critical density. And so we're going basically into the range of classically near critical plasmas. And so fortunately, because of the higher upper limit due to the higher laser intensity, there is still a wide range of densities that can be used. But what this estimate indicates that when we're talking about shorter laser pulses, we are necessarily dealing with plasmas that should be produced maybe using foams or other high density materials. Now, here's an example to illustrate this relativistically induced transparency in a 3D particle and cell simulation. In both cases, the plasma is the same. It is located within the rectangles on the right. The difference here is that the laser pulse in the lower panel has an amplitude that is 2 orders of magnitude higher. So you can see that because of that, the laser pulse is actually able to penetrate the plasma instead of being reflected like in the upper panel. And so as the laser pulse goes into the plasma, it pushes the electrons forward and drives a volumetrically distributed longitudinal electron current. It is shown here in blue. As you can see here that the electron current density is really high, so that when we integrate over the entire cross-section here, we find that the total current is close to 2 megaamps. In order to prevent significant charge separation, the plasma produces a return current, but this return current, shown here in red, flows on the periphery of the laser beam. And so there is really no compensation between the laser-driven current and the return current. And this is what allows for the current to generate a very strong magnetic field. It is shown here. It is impressive already in terms of the absolute value, because in this specific example, it is roughly half a megatesla. But what is also unprecedented here is that this field is actually competitive or comparable to the laser field. It is 10% of the peak laser magnetic field. This magnetic field, since the current is longitudinal, is azimuthally directed. So it looks like it is coiled around the laser beam. And so this is why, as we go forward, I will refer to this as a magnetic filament. Now, one more thing to point out here is that the laser magnetic field is oscillating while this magnetic field is evolving very slowly on a time scale of laser oscillations. It still remains to be seen if this approach can be effectively scaled up to get to magnetic fields much greater than 1 megatesla. And of course, another interesting topic of how this magnetic field can be detected inside the plasma. I deliberately left this out of the talk because we still have a lot more material to cover. Now, when we're talking about generating these fields, we're necessarily talking about using tightly focused laser beams as shown here. So in this simulation, such a beam irradiates a uniform plasma target with an electron density equal to 30 and critical. Now, due to tight focusing, the laser beam expels electrons laterally, and due to high ion density, the ions follow actually quite quickly. And as you can see, we produce an almost fully evacuated channel. The blue curve here indicates the surface where the electron density is equal to the critical density. Now, since this is a 3D simulation, if we look in the transverse plane, this is the XZ plane, we also see that an instability starts to develop with the laser deviating to the side. So the takeaway point here is that, unfortunately, a long-term interaction can become ineffective in a dense uniform plasma. Now, again, it is helpful to put some real numbers here. So if we're talking about Eli NP, then a 30 femtosecond laser may not be affected by this phenomenon. But if, for example, we decide to use the same approach using the L4 beam at Eli beam lines, we would necessarily run into this problem. And this is what motivated us to look for alternative or constructive solutions. One such solution might be to use an advanced target. Here, I'm specifically focusing on using structured targets. So these targets in the bulk, they are relativistically near critical. And they have a cylindrical channel that is filled with a material that is still dense, but has a density that is lower than that in the bulk, so that it becomes relativistically very transparent when irradiated by a high-intensity laser pulse. In this 3D PIC simulation, you can clearly see the benefits of using such a structured target. So first of all, it clearly, by guiding the laser pulse, it stabilizes its propagation. Now, since the transverse laser electric field continuously extracts electrons from the wall of the channel, it essentially replenishes the electron population. And you can see here that the channel remains filled with a dense plasma as the interaction continues, which basically extends our laser plasma interaction, which will be critical for the topics that I would like to discuss next. Now, the targets might look very exotic, but a lot of progress has been made in the last several years in the field of target manufacturing and target fabrication. And in fact, these exact targets have already been manufactured by General Atomics. Here you can see some of the snapshots, and they have been already used for a first experimental campaign performed at the Texas Petawatt by Hans Rinderknecht. The paper is currently under review with the New Journal of Physics, but if you're interested to take a look at the results, I recommend this archive publication. Now, as we have seen, by using dense targets and high-intensity lasers, we can generate very strong magnetic fields. These magnetic fields can be effectively leveraged to produce dense gamma ray beams and energetic electrons. And this is what I would like to talk about next. So now when energetic electrons travel along our magnetic filament, they experience transverse deflections. And as their trajectory bends, they emit electromagnetic radiation in the form of X-rays and gamma rays. The emission process can be described using a dimensionless parameter. I call it here eta. It is proportional to the product of the electron gamma factor and the magnetic field that causes the deflections. Now the emitted power goes up as eta squared. The ratio of the photon energies that are emitted to the energy of the emitting electron is equal roughly to 0.4 eta. So you can clearly see that there is an advantage of going to higher etas if you would like to emit at higher power, higher energy photons. Now, again, let's look at some specific examples. If we're using a conventional magnetic undulator with a field strength equal to 1 Tesla, then we can use 10 GeV electrons produced by a linear accelerator. And as they get deflected, based on this expression, they're expected to generate 10 keV photons. And this is in fact exactly how the European X-ray free electron laser operates. Now, by going from this traditional magnetic field to a plasma-generated magnetic field of 0.5 megatesla, we can increase the photon energies by 2 orders of magnitude from 10 keV to 1 MeV while using significantly lower energy electrons. So in this specific example, 100 MeV electrons would emit 1 MeV photons. Now, the advantage here is that if we need only 100 MeV electrons, then we no longer need a linear accelerator. And potentially, such electrons can be generated using the same laser-plasma interaction that we're discussing. Now, before I show you that this is indeed the case, it would be useful to discuss how we go about simulating the emission process, because it is far from straightforward. And the problem comes from the fact that the wavelengths of the emitted photons is extremely small. So for 1 MeV photons, the wavelength is 10 to the minus 3 nanometers. Now, if we're using a highly resolved particle and cell simulation that has 100 cells per micron, the cell size would be 4 orders of magnitude greater than the photon wavelengths. So what this tells us is that the photon wavelength is way too small to be resolved in any realistic scenario using a conventional particle and cell code. Now, there is, of course, another scale length in the problem. It is the distance between the electrons. Now, even for a plasma with an electron density equal to 50 and critical, this distance is 2 orders of magnitude greater than the photon wavelengths. What this means is that the emission, therefore, can be treated as incoherent. And this observation is the foundation for the development of the so-called QED particle and cell algorithm. So this algorithm emits high energy photons as individual particles. Now, since the emitting electrons are very high energy electrons, they emit into a very small opening cone. And so the algorithm simplifies this by emitting photons in the direction of the electron momentum. As the electrons emit photons, they experience a corresponding recoil. Typically, the photon emission is simulated using a Monte Carlo module based on QED synchrotron cross sections. And this is exactly what was done in the simulations that I will show you in a couple of slides. Now, as we already mentioned, in order for these high energy photons to be emitted, we first need to produce high energy electrons. The electrons in the considered setup gain their energy from the laser electric field, and primarily it is the transverse laser electric field. Now, the electrons gain energy only when the velocity is anti-parallel to the laser electric field. Otherwise, they're losing their energy. Here are some representative electron trajectories from our particle and cell simulation. So when the electrons are extracted from the wall and start gaining their energy, because the laser magnetic field is very strong, they experience a strong forward push. So they are actually flying forward with the laser while gaining energy. This definitely prolongs the acceleration process, but the electrons are still moving slower than the laser wavefronts. And so they're slipping and gradually slipping out of the phase that is favorable for the acceleration. So the so-called dephasing is the mechanism that ultimately terminates the energy gain in the absence of the magnetic field. Now, the presence of a strong magnetic field qualitatively changes the interaction due to the transverse deflections, because these deflections can flip the direction of the transverse electron velocity and therefore mitigate the negative effect of the dephasing. In fact, this is exactly what is happening in this particle and cell simulation, where the electrons are able to achieve values of the gamma factor that are greater than 1200. And this is for a value of A naught that is only 50. To get a better insight into this energy enhancement mechanism, we have developed a test particle model. So in this model, laser fields and the plasma magnetic field are treated as input parameters. So we approximate the laser pulse as a plain electromagnetic wave, and the plasma magnetic field is a field generated by a longitudinal uniform current. Here you can see results of a test particle calculation. You're looking at the electron gamma transverse electron displacement and the laser electric field at the electron location as a function of time. What is shown here with yellow is the part of the trajectory where the electron velocity is anti-parallel to the laser electric field, and therefore the electron is gaining energy. Let's, for example, take a look at this one oscillation of the laser electric field. What we see is that due to the deflection, the magnetic field keeps the velocity anti-parallel to the laser electric field. So during the entire period, the electron is actually gaining energy. Now, you can see that this is the electric field at the electron location. So it oscillates while the gamma factor increases. So this means that the electron energy gain continues while the electron is slipping with respect to the laser wavefronts. And this is what I mean by the magnetic field mitigating the negative effect of the dephasing. And this prolonged energy gain leads to a dramatic energy enhancement, even for electrons that are injected with a significant transverse momentum. In this example, the electron can reach a gamma factor that is roughly 5,000. So this does look very promising. The main question is, what kind of electron density or what kind of plasma current do we actually need to drive in order to get into this regime? The answer to this question can be obtained using the same test particle model. Here you're looking at the maximum gamma factor that the electron achieves during a single half bounce across the filament. So the electron starts on axis and then comes back to the axis. What this test particle model reveals is that there is a universal dependence of the energy gain on the initial momentum with which electrons are injected and the plasma current. Here it is represented by a dimensionless parameter alpha that normalizes the current through a cross-section equal to pi times the laser wavelength normalized to the classical Alfvénic current. Now, for the purpose of this presentation, what is important here is that there is this dark region, which means that if the current density is not sufficiently high, then not all initial injection momenta would lead to a significant energy increase. Therefore, we can conclude that for the purpose of generating a lot of energetic electrons, the preferred regime would be located here in the upper part of the diagram, where the dependence on the initial momentum essentially disappears. This condition can be, and it is more convenient to recast it in terms of the electron density by assuming that the current is generated or consists of relativistic electrons. So what does this condition mean? So let's take a laser pulse whose A naught is equal to 100. This means that the plasma must be at least near critical to get into this preferred regime. And this is yet another argument for using foams inside the target instead of using a gas target, because using a gas jet, we would not be able to get into this regime. Now, the electrons are able to continue gaining energy through this mechanism for as long as they remain within the laser beam. Now, they are being confined within the laser beam by the magnetic filament itself. Using the same test particle model, we have derived an expression for the maximum amplitude of the transverse electron oscillations. We call it the magnetic boundary because this emphasizes that the confinement is provided by the plasma magnetic field. What is important here is that the location of the magnetic boundary depends on the product of the electron gamma factor and the relative degree of superluminosity. Now, the superluminosity is unavoidably caused by the presence of the plasma itself. In our PIC simulations, we typically observe that the relative degree of superluminosity is at the level of 10 to the minus 2. Now, for an electron that is injected with an initial gamma factor that is 0.1 of A naught, which is quite reasonable because, of course, the injection occurs due to the interaction of the transverse laser electric field with the walls of the channel. Now, as the gamma factor increases at about 10 A naught, this contribution becomes competitive and plays a role, and this means that the magnetic boundary should be expanding. This is exactly what we see by tracking the particle trajectories in our three-dimensional particle and cell simulation. The color here indicates the particle energy. You can see that the expansion does occur due to the superluminosity. Now, as the particle trajectories expand, the particles might reach the edge of the magnetic filament and therefore become lost, which would prematurely terminate their energy gain. Now we can reframe this negative message into something positive. So let's say that we want to increase the electron energy, but we're not able to go to significantly higher values of A naught. What this observation tells us is that we might be able to improve the situation by using a higher power laser. Because by using a wider beam, we would have a wider magnetic filament, increase the electron confinement, and therefore potentially increase the photon yield. To confirm this, we have performed such a scan where the value of A naught is the same, it is 190, and we're looking at lasers that have a different power. Since A naught is the same, the power increase is achieved by making the laser beam wider. The channel is widened as well, just in order to make sure that we utilize the entire power of the incident laser beam. As you can see here from the electron spectra, as we increase the laser power from 1 to 2 to 4 petawatt, the electron spectrum becomes much more energetic due to the improved electron confinement, with the maximum gamma factor being as high as 2000 here. Now, as the electrons become more energetic, they emit more, and you can see that the conversion rate of the laser energy into the energy of multi-MeV photons, these are the black markers here, goes up considerably with power. The increase is even more dramatic for higher energy gamma rays. So the blue markers show the gamma rays with the energy above 100 MeV. The increase here happens because we're producing higher energy electrons. Now, once we reach the 4 petawatt level in this specific example, we see that there is this saturation or rollover that occurs. It happens due to the beam filamentation. So the way to understand this is to think about this as a scenario where we are reverting to smaller beams. Now, the main point here is that using higher power laser, even without increasing A naught, would be beneficial. And so this is why it would be beneficial to go to doing these experiments at higher power laser facilities, even if the value of A naught is still in the range of 190. Now, in this specific example, the optimal power is 4 petawatt. And in this case, we do produce a beam of highly collimated gamma rays. In fact, the beam consists of 2 highly collimated lobes. Here you're looking at a projection of the photons with an energy above 1 MeV onto a sphere. So each green circle here corresponds to a cone with an opening angle of 10 degrees. And in fact, the conversion rate that I showed you on the previous slide represents the conversion rate into a single lobe, which makes the absolute numbers here even more impressive. So just a single lobe here represents 1.5% of the total incident laser energy. And it corresponds to more than 10 to the 12 multi-MeV photons emitted within a single cone. It is worth pointing out that if we integrate actually over the entire 4 pi angle, the conversion rate can be a lot higher. And this is what is often reported in some publications. But of course, for the purpose of applications, we're probably primarily interested in these highly collimated beams of gamma rays that we can produce. One application that can really benefit from such a beam is the production of matter and antimatter from light alone. And this is the last topic of my presentation for today. So if we are interested in producing electron-positron pairs in vacuum, we can think of two possible concepts. One is to collide these gamma rays with black body radiation. Another one is to collide one gamma ray beam with another gamma ray beam. Now, if we're talking about facilities like ELINP that have two high power, high intensity short pulse lasers, the second approach is probably the way to go. We have examined this scenario. So in this case, we're using two 4 petawatt lasers, each creating a gamma ray beam using the mechanism that I've just described. And these gamma ray beams collide 250 microns away from each of the targets. Here you're looking at the rate of the pair production as a function of the photon energy. So again, here, two photons collide to produce electron-positron pairs. Now, when we're talking about these gamma ray sources, it is important to remember that the gamma ray spectrum is actually quite wide. And for some applications, it might be viewed as a disadvantage. But in this case, it actually works to our advantage. To illustrate that, let's take a look at this part of the plot. So here, 100 keV electrons are producing pairs. Of course, 100 keV, sorry, not electrons, photons, on their own, they're completely useless because they cannot collide and produce pairs because they do not satisfy the energy requirement. The reason why we're able to utilize them is because we have a high energy gamma ray tail. So in this case, it is 10 MeV photons collide with 100 keV photons, making them suitable for this energy requirement. And this is how significantly more pairs are produced. As a result, this kind of approach is able to achieve roughly 10,000 electron-positron pairs. Now, for the purpose of full disclosure, I should mention that this distance is important and it is a significant limiting factor because as we maybe double or triple it, the yield goes down considerably. Motivated by trying to increase the yield, we started looking for alternative concepts, and we realized that probably the best way to go is to relax the requirement that we should be producing the pairs in vacuum. Why don't we try to produce the pairs inside a plasma? If we go in that direction, then we can consider the same structured target that is irradiated by two counterpropagating laser beams. Now, the advantage of using a structured target is that it would provide us with automatic alignment that can be very difficult to achieve if we're working with a gas jet. Now, each laser beam produces a group of energetic electrons that travel with the laser. Once the lasers collide, the electrons from one of the beams collide with another laser beam head-on. And more emissions occur when this collision occurs because the parameter eta that characterizes the emission goes up. You can clearly see it in this plot that shows the evolution of the eta distribution in our simulation. So before the collision, the value of eta is primarily determined by the plasma magnetic field. During the collision, it is determined by the laser magnetic field that is several times higher, hence this jump in eta. Now, as eta jumps, the emitted power jumps as well, and so the electrons rapidly radiate a huge part of their energy. You can clearly see this where you're looking at the time evolution of the electron distribution function. So the point here is that due to the collision, the emission becomes highly localized. Now, on top of that, the collision also increases the conversion efficiency. You can see it in this plot where the blue markers show the conversion prior to the collision and the red markers show the conversion for the entire interaction. Now, all these factors combine to dramatically increase the photon density after the collision. You can clearly see it here that for the photons with an energy above 1 keV, it exceeds 600 times the critical density. Now, since the photons are produced by counterpropagating electrons, the photons are counterpropagating as well, and this opens a very attractive opportunity where the photons at a very high density can collide inside the plasma and produce electron-positron pairs. Now, of course, this would work only if the two photon pair production mechanism is the dominant one. It does have some competition. First of all, the gamma rays that we produce can interact with the Coulomb field of the ions and produce pairs that way. This mechanism can, or its importance can be reduced by reducing the volume of the bulk material and also by using the high Z, by using lower Z ions. The real competition comes from the nonlinear Brightwheeler process. This is where the gamma rays collide with the photons of another laser. Fortunately, particle and cell codes these days are equipped with a module that can easily evaluate the yield of this process, and this is how we obtained the pink markers here. They show the total number of pairs produced in our simulation as a function of A naught. What is actually difficult to calculate is the yield from the linear Brightwheeler pairs. And this is because this would require us to evaluate binary photon collisions. And as you've seen, we do produce a lot of photons. Currently, none of the particle and cell codes can do this. So we had to develop our own algorithm. This is a post-processing algorithm that uses the data from the PIC simulation. It groups the photons into beamlets that consist of photons with the same energy, and then we check for the collision of such beamlets. So it is computationally a lot more affordable, and this is how we were able to calculate the yield shown here with the green markers. What is really striking here is that unexpectedly, the yield from the two photon pair production actually dominates at experimentally relevant laser intensities. What is also really striking here is that in terms of the absolute numbers, we can produce over 10 to the 8 pairs via the linear Brightwheeler process at the experimentally achievable intensity of 4 times 10 to the 22 watts per square centimeter. This is 10,000 times more pairs than what we can produce by colliding the gamma rays in vacuum. By using the same algorithm, we found that most of the linear pairs are produced within the channel. Therefore, they're produced within the magnetic filament. Now, the magnetic filament retains its polarity after the lasers collide, which means that the polarity with respect to each of the laser beams is now reversed. This is what is shown in this animation. So this is the quasi-static magnetic field. Now, as the lasers collide, you can see that the polarity remains the same, but with respect to each of the beams is now reversed. What this means in terms of the particle confinement is that the field can now confine generated positrons moving with each of the laser beams rather than confining the electrons. And here you're seeing this for the nonlinear Brightwheeler positrons produced in the PIC simulation, but the situation is expected to be very similar for the linear pairs. Now, as the positrons are moving with the laser beam within a magnetic filament, they're subject to the same mechanism that we have discussed earlier for the electrons. And therefore, their energy can be increased. You can clearly see it from this plot, where this is the distribution of the positrons in energy as a function of time. So as the time increases, the positron energy goes up, and it can be as high as 1 GeV when the positrons leave the target. Nothing similar happens to the electrons because they're actually no longer confined. So the main point here is that nonlinear Brightwheeler positrons form ultra-relativistic jets gaining energy from one of the lasers. We expect for the situation to be very similar for the linear Brightwheeler process, but more code development is needed to generate linear Brightwheeler pairs during the PIC simulation and to assess this mechanism self-consistently. So this brings me to my last slide. Hopefully, I was able to convince you that laser matter interactions at multi-beam, multi-petawatt laser facilities have the potential to enable qualitatively novel regimes characterized by megatesla magnetic fields, dense multi-MeV photon populations, and matter and antimatter creation from light alone. At this point, I would like to stop, and I'm happy to answer any questions that you might have. If you do not have time to ask all the questions or to provide all the comments, please feel free to contact me directly by emailing me at UCSD. The email is given below. So I'm stopping here. Thank you very much for your attention.
Thank you very much for the wonderful talk. So yes, please enter your questions in the chat field or signal to me that you would like to ask a question. And also I'd like to give a nice thank you applause and give some applause emojis. So we do already have a question in the chat from Yuan Shi. In QED PIC, it might be easy to tell which process produced the positrons. In experiments, how would you be able to tell you have seen the linear VW positrons?
Oh, so of course, the only way to know that you're producing actually the linear Brightwheeler positrons is to go to lower intensity. So this is the main takeaway point here, because at intensities of, let's say, several times 10 to the 22, you would not be able to produce nonlinear Brightwheeler pairs. So you could see that the rate is actually very, very low. And so if you're seeing those jets, then you can infer that they're coming from the linear Brightwheeler pairs.
So I have a question. At the beginning of your talk, you were talking about producing very large magnetic fields of order 10 to the 6 Tesla, which is larger than the atomic unit of the magnetic field. And so I was wondering if you thought at all about being able to study atomic physics in that regime, which I think would be really neat, and maybe implications for EOS of like the outer shell of neutron stars or warps.
So this is a good question. So I have thought a little bit about that, but mostly due to I do not have the background in nuclear physics, so my experience with that is limited. But I think this is definitely one of the promising directions, and this is why people are we're discussing this more like a platform for doing high field physics. So like one of this can be exactly as you said, using this very strong magnetic field for looking at some nuclear physics.
I was talking about the atomic physics.
The atomic physics, yeah. Oh. But one issue can be that, of course, the laser intensity is so high that we're likely to ionize everything. So when we first started thinking about this, it's not exactly clear what would be the best setup to utilize such a magnetic field, because of course it is, at least like initially, it is co-located with the really high intensity laser pulse, which would probably extract most of the electrons from even very high Z ions.
Yeah, I'm not sure what will be left then. but there's got
But I
to be
mean,
interest. Yeah.
it's definitely worth discussing, and so I probably would like to discuss this like after the talk, because I mean, my training, I'm trained as a plasma physicist, but there are always a lot of interest in overlaps, and I'm definitely interested in exploring such an overlap, because this would produce an unprecedented magnetic field. So finding useful ways of leveraging that would definitely be beneficial for that research and for motivating us to do more of our plasma physics research as well.
Hmm. So there's another question from Yuan Shi. Do the QED cross sections in PIC take into account the effects of strong magnetic fields?
So so some of the cross sections do take into account, the others do not. And so actually the fact that we are talking about the pair production inside the plasma, so let me maybe like rephrase this. So previously people looked at pair production in a vacuum, and so in that case the cross sections are typically known. Now if we're seeing that there is a lot of promise in the regime where we're producing things inside the plasma, we're hoping that this would motivate people to examine the strong field corrections and the plasma corrections to the cross section for the pair production. So some of this has not been done, and the new regime that we have discovered, that I just presented at the end of my talk, is likely to stimulate people to re-examine the cross sections and to see if there are like any consequences in terms of the corrections or not.
Are there any other questions?
Alex, this is Hui. Thank you for your talk. May I ask a question?
Of course, of course. Hi.
Hi. So I understand that you need a large anode. Did you try? What's the lowest threshold you could go to still drive high magnetic field? I'm trying to follow up with pulse, atomic physics.
So what we found with the magnetic field, that it, like under different setups, the magnetic field can basically, the scaling for the magnetic field can be maybe like 5% of the peak laser magnetic field. So by reducing the intensity, we can still get to a very strong magnetic field. So you basically have to maybe divide what you get for the laser by a factor of 20, and this is what realistically you can expect. We have never seen anything. So in terms of when we look at the energetics, it seems that in principle it is not possible to really, in this case, drive something much stronger than the magnetic field of the laser itself. So that would be the upper limit already, and typically it is never higher than 20%.
Well, if you could, I was just wondering if even 20% of laser field is a pretty impressive magnetic field. So the point is, if you could extend the pulse length, so basically somehow have a plasma with, time scale is much faster in simulation than the collisional time scale. So if you could somehow use an extended pulse and have the magnetic field stay a little bit longer, so we have a plasma have very strong magnetic field, given 1Z, that could be a pretty interesting platform to, for the things we care. And what I mean, let's say atomic level.
We should definitely discuss this more, because it is something that I wanted to look, because what we do see in the simulations actually is that even when the laser is gone, the magnetic field can persist for quite some time. So usually, let's say like in the channel, the laser passes and like it goes further into the target, and we can see that the magnetic field stays, and it can remain usually until the end of the simulation for at least like hundreds of femtoseconds. And we never even ran long enough to see for the magnetic field to go away. But of course, the simulations are collisionless, so that can be like one of the limitations. But there is definitely promise for that. So it's not like the magnetic field is there only for as long as the laser is there. You just need the laser to kind of like to get this process going. And once the magnetic field is there, the plasma seems to be happy to sustain it even when the laser is gone.
Thank you very much.
Yeah. So Alex, to follow up on Hui's question, I'm wondering whether atomic physics could be utilized to actually help characterize the magnetic field. For example, using the Zeeman splitting. Do you have any thoughts on that?
So I guess the answer would be yes and no. Like I am interested in this. I have discussed with some people, but so far it hasn't gained enough traction. So if Mingsheng, if you know somebody who's qualified and who's interested to discuss and maybe looked into this much closer, I would very much be interested to examine that, because the simulations can be easily rerun with a high Z material, and we can, because the field ionization is included in the code, so we can actually see like how many electrons we're able to rip out and who stays, and so then we can realistically like predict like how many electrons are still inside the atoms or like inside the ions, and what kind what we can actually expect in terms of the splitting. Because I do think that this would be very promising, because as I only kind of like implied earlier, that the big challenge when we're talking about high field physics inside the plasma is that when we're dealing with a very dense plasma, we have no way of really directly knowing or seeing what is going on inside. So, and when the magnetic fields are that strong, it is very challenging to measure them using traditional techniques. Let's say we cannot use energetic protons to measure them, because all of them will just get deflected and will never even penetrate that region. So finding kind of creative ways like Zeeman splitting to characterize the magnetic field would definitely be a huge advantage for, just again, to gain more understanding of what is going on. Because of course the simulations do provide some insight, but until we actually measure and see things for ourselves, and I mean, maybe there would be some surprises on the way as well.
So Alex, this is Scott. I have a quick question. Can you explain, maybe using a physical argument, how the orders of magnitude difference in the cross section between the gammas with the Coulomb field and the gammas with themselves switched? Somehow they seem larger for gamma gamma, and I don't understand quite how that happened. I would still think in a plasma that the cross section would be much higher for the gammas to interact with the Coulomb field of the ions there.
To produce the better Heitler like pairs, right?
Yeah, right.
Yeah. So so first of all, the density. So like when we're talking about the channel, so the density there is maybe 10 to 20 in critical, and so like because of that, we don't really have that much material there, and so this is the like the primary motivator. So if we significantly increase the volume of the bulk, then it will drive that up. So like when we typically estimate this, like so we take, so like inside the channel the density is 20 in critical. So let's say like if everything is propagating along the channel, so you take 20 in critical times like 100 microns, and then the yield is low. It would be high if we're hitting the walls, but basically by taking it as a tube instead of taking like a 1 centimeter cubic target and drilling a 10 micron hole. So that would be definitely detrimental to doing this. Now,
I see.
Another thing that this is actually like a very good question. So there is another way to discriminate between that signal and the two photon pair production, because when the gammas will interact with the Coulomb field, they will produce the pairs volumetrically, and most of those pairs would be produced outside of the magnetic filament. So then no acceleration can occur. Now, most of the two-photon pair production happens inside the magnetic filament and therefore inside one of the laser beams. And as a result, those pairs would be confined, and then they can basically get ejected as ultra-relativistic jets of positrons versus being basically sprayed all over the place.
I
So
see.
by looking at that, so of course, I'm not an experimentalist, and I understand after talking a lot about this with Hui that there are a lot of challenges of doing something even like remotely similar to this. But
Sure.
the difference in this experimental signature can hopefully be very helpful.
Yeah, but I see your point is that your idea is, hey, I'm going to localize the plasma so small that the mean free path of the gammas is going to be such that they're not going to have time to interact with the Coulomb field.
Yes, that's exactly the point. Yeah.
Yeah. Okay. Good. Thanks so much. Great talk, by the way. Thanks.
Thank you.
So thank you again, and I hope there's lots of discussion. It sounds like some people might be interested in discussing how to take advantage of this platform.
And I'm definitely interested in exploring this more. So this was a great opportunity to present this to a lot of experts, because we are definitely looking to for some intersections and for opportunities to collaborate, especially if it is outside of our area of direct expertise.
Yeah. And I'd like to thank you again, and
thank you.
And thank you everybody for attending, and hope to see you next week.